Okay, so we'll continue our discussion, and we are starting to make into our foray into Tomita-Takesaki theory. So we'll see glimpses of the main Tomita's theorem today. Okay, so before that, I just wanted to make a couple of remarks. So in the previous time, we defined von Neumann algebras. We kind of motivated the definition using CG modules. So I just want to correct myself a little bit. We had a dictionary. So there I had said that if I'm thinking of a cyclic vector, okay, so let me define what a cyclic and separating vector is. I had mentioned it without defining, so let me do that now. So let's say R is a von Neumann algebra acting on the Hilbert space H. So then a vector V in H is said to be cyclic for R, is said to be cyclic or generating. So these are the common terminology you'll see, or generating. If RV, if you take, so RV will be a vector space, it's dense in H. So, or if you take closer, RV is equal to H. Then V is said to be generating for R. So I should say for R. And similarly, you have another notion known as separating. V is said to be separating if whenever you have AV equals 0 for some, so separating again, like it is separating relative to R. So this vector is called separating for R. If whenever AV is 0 for some A in this von Neumann algebra R, we must have A is equal to 0. So that is the only way you can have AV is 0. Then A must be 0. So that is the notion of a separating vector. So now the connection with representation theory, I want to clarify a little bit. So there is something known as the regular representation. So anytime, so the analogy was with finite groups and looking at the complex group algebra. So this was the one that was looking like our R. And then this was, if G had a representation, whichever space it was acting on was like our Hilbert space H, right? So when we are thinking of like a left regular representation, the vector space, the V was actually CG itself. And CG acts on V via left multiplication. So that is the left regular representation. So in this context, so here, this representation actually has a cyclic and separating vector. So let me point that out. So if I look at the vector V is equal to just the identity element of the group, or you can just write E, for, let's say E in the group. So if I take this is actually a cyclic and separating vector. So cyclic simply because it's a left regular representation. E moves around and gives you any element. So this is cyclic for the left regular representation. And also separating. So separating because if you look at any element here, it is just a formal linear combination of elements of the group. And these you can think you have some delta functions on each of the elements. So CG you can interpret in that way. So essentially it's a set of functions from the set, the group to complex numbers. So you can think of it as a set of functions. And then, so separating follows from the following fact. So if AV is 0, that means you have a summation AG, G. This is equal to 0, right? So it is literally saying that, and G multiplied with E will give you G. So it's just saying this is 0, which means all these coefficients must be 0. So it's a straightforward fact. So for left regular representation, you have a very natural choice of a cyclic and separating vector. So now let's look at any other representation of CG. So then if you take a vector V, and I can always map 1 to V. So let's say I have some V is some vector. So I have a map, taking identity to V. So then you get a map from the left regular representation to the representation that you care about. Let's say you have, so I think I should have set up the notation. So let's say rho is a map from CG to something like MNC. So this is a representation. And then you have the left regular representation that naturally comes with the C of G. So what I can do is if I pick a vector v inside C to the n, I have a map taking 1 to v, and the way I have a homomorphism between these two representations is I will send any element of this form to g dot v, right? Any element g dot 1, I'll just send 1 to v, and whatever action you get from this group and the complex group algebra, I'll do the similar action here. So then what does being cyclic and separating mean? If v is cyclic, this means the map is surjective. Map is surjective, right? So what this is telling you is that your representation, which was on here, this representation is a quotient of the left regular representation. So let me just say, so if v is cyclic, so v being cyclic implies your representation is isomorphic to a quotient. I had in the previous dictionary, I had written it is actually something inside. It's not really inside, it's something smaller than the left regular representation. But roughly that was the idea I was trying to say. So your representation is a quotient of the left regular representation, which you can think of as being a smaller thing than the left regular representation. Now, if you take V separating, then what do you get? Here you get surjectivity. So if you take separating, then you will get injectivity. So this map 1 going to V. So here this was the kind of the cyclic and separating vector for the left regular representation. So if you send 1 or E, as we called it, to V, then this is injective, because what it is trying to say is if this element, this action is going to AGGV, right? So what is the kernel? Kernel would mean that this is equal to 0, but we are saying that this is equal to 0 if and only if this is already 0. So that's exactly, so V separating implies, in this case, it is correct what I wrote. This implies that your left regular representation is inside, it's a sub-representation. Left regular representation is a sub-representation of whatever representation you started off with, from which you had chosen this vector in the represented module. Yeah. So left regular representation is a sub-representation of your representation, whatever you started off with. So anytime you see this assumption in the literature that's saying that let R be a von Neumann algebra with a cyclic and separating vector, if you put them together, so existence of a cyclic and separating vector just means that your representation is isomorphic to left regular representation. So existence of cyclic and, so that same vector is both cyclic and separating. So existence of that implies your representation is isomorphic to the left regular representation. So carrying this analogy forward in von Neumann algebras, typically when you're thinking of like let R be represented on a Hilbert space which has a cyclic and separating vector, you're thinking that it's like a standard representation or a left regular representation. And all the intuition that you may have from your older representation theory, you might want to push forward. Okay. So this is the clarification I wanted to make about the dictionary. So we'll come back to hopefully at the end of this lecture, we'll come back to this, the idea of cyclic and separating vectors and what it means in the context of Tomita-Takesaki theory. But before that, we'll go to the main theme of today's lecture, which is what in the email I had mentioned, which I'll call the Gardner phenomenon. So what's the Gardner phenomenon? I'll give you first an example and then we'll do proofs. And eventually, Tomita's first theorem will essentially be a consequence, or at least it will help you guess why such a theorem should hold. Otherwise, it looks very mysterious, the first Tomita's theorem. But if you understand the Gardner phenomenon, it becomes clear that you expect. But in order to make this phenomenon work out in the unbounded operator case, a lot of work has to be done. So that's why I'm not saying that just because you guessed the answer, that means you already have the answer. A lot of work still needs to be done. But if you are familiar with this, you will be able to guess this. So that's where we are headed. So what's the Gardner phenomenon? Let me give you a quick example. So let A, B, so be bounded operators, self-adjoint operators over some Hilbert space. And let T be an invertible positive operator. Let T be positive. So let T be a bounded operator, which is positive and invertible. Okay. Sorry, of course, there is a connection between this A, B, and T. It's not just, I'm just writing symbols here. So T is positive and invertible such that these are actually similar operators. TA T inverse is equal to B. So A and B are self-adjoint, and you have TA T inverse is equal to B. So now, since it is in fact, this statement you can also write for any C-star algebra. It has nothing, because any C-star algebra anyway embeds inside B of H. By the end of this statement, you will be able to already see that it holds in any C-star algebra. Because if any T is positive and invertible, sorry, I didn't mean positive. Forget this. A positive operator will appear once I do the polar decomposition. But sorry, so T is just assumed to be invertible, such that TA T inverse is equal to B. So now I have a unitary polar decomposition in any C-star algebra. If T was in a C-star algebra, simply because T is invertible, right? If you, yeah. So let's say this is the polar decomposition. So you have this unitary and you have this positive operator, and this H is actually an invertible positive operator. So now what can I say? Let me rewrite this. So I'll just replace T with U of H. So I have this U star is equal to B. Now I'll just play around a little bit. So H inverse is equal to U star BU. So by our assumption, B is self-adjoint. So if B is self-adjoint, U star BU is also self-adjoint. So I can also write it as U star BU whole star, which means I can write it as H inverse whole star. So all things concluded, all things combined, what I have concluded is that H inverse is equal to H inverse AH, right? Then I move the H's around. So this implies H square commutes with A. So A is self-adjoint, H is a positive operator, you have this. That means if I take any polynomial in H squared, then that also commutes with A. And now you can probably fill in the details if I left it here, but just to finish my thought, that means if I have any continuous function with certain properties, I can approximate, in particular, the square root function I can approximate using such polynomials. So that means H of A is equal to A times H. So in fact, A already commutes with H. And here. So what does that tell me now? So UA U star. So let's go back to what we had here. So we had H inverse is, yeah. So H inverse, this will cancel, like I can move H around, so it will cancel off. So what I have concluded is that UA U star is in fact equal to B. So I started off with just similarity using, it's just some invertible operator. But now what I have concluded is that, so similarity implies unitary similarity. So similarity of self-adjoint operators. So if two self-adjoint operators are similar, they must actually be unitarily equivalent. Implies unitary similarity. Of course, this is not true for general matrices. And you can think you have Jordan canonical form on those things, and the norms don't have to be bounded in the similarity orbit. But for self-adjoint operators, this is something you have. Okay, so this was just about a single operator. It was about not single, a pair of operators, pair of self-adjoint operators. We are going to, the Gardner phenomenon is a generalization of this. You can think of it that way. And let me state the invariance theorem first, which is the main goal of today's talk. So this is the Gardner's invariance theorem. It says that you can make the similar assertion for any self-adjoint subspace. So actually, that will be a corollary, but a little bit more general statement than that. So let S be a norm-closed linear subspace of B of H. And T be a positive invertible operator. So here I need both positive and invertible. So T be a positive invertible operator in B of H. Then if TST inverse is equal to S as sets, meaning S is invariant under this conjugation. So S is just similar to itself under this T. So S is invariant under what I'll write as T tensor T inverse. So think of this as a map from B of H to B of H, meaning whenever you take an element A, so the way this will act on an element A is that just it will send it to TAT inverse. So if you think this is just a notation I'm using, of course, as tensor products of operators, you can think of it like if we had a, like if this was like in the matrix case, of course, you can think of it that way because you have the Hilbert-Smith operators, which you can think of as tensor products of certain Hilbert spaces. You have this H tensor H bar is isomorphic to operators, so B of H. So if H is finite dimensional. So that's how you get the class of Hilbert-Smith operators. So otherwise, you'll have some Hilbert, instead of B of H, you'll have the Hilbert-Smith operators. So if you are in such a case, you can interpret it actually as a tensor product of operators. Otherwise, just think of it as a definition. T tensor, anytime I have a tensor B, the way it will act on X is it will send it to AXB. It's a bilinear map and so on. Okay. So what I'm saying is S is invariant under this map. So it's an invariant subspace of this. Okay. Then the conclusion is, very nice conclusion, then T to the Z, S T to the minus Z is equal to S for all complex numbers Z. That is, I mean, again, rewriting in this terminology, that is, S is invariant under T to the Z tensor T to the minus Z. So if I plug in Z equals IT, what do you get? You get a unitary here because T is positive, T to the IT will give you a unitary. So again, it's a reflection of that fact. It's just saying that if S is, you have T implementing some sort of similarity between S and itself, then you have a unitary, which will also, and you have actually lots of unitaries. You have T to the IT for any T. So you have a automorphism group sort of, which will leave this as invariant. And as a quick corollary, let's note the corollary first, then we'll try to prove the theorem. And so similar to what we did in the previous time. So the corollary goes as follows. A, B, let they be self-adjoint subspaces of B of H. And T be a positive, T be an invertible operator. So we'll be using the polar decomposition theorem, be an invertible operator such that it implements the similarity between A and B. So there is a T such that as sets you have this similarity. Then actually A and B, there are many unitaries which will implement this similarity. So actually, in a way, this is a proof rather than, so statement is kind of contained in this proof. Assuming that theorem, we have this proof. So let T equals U of H, same story. We'll just, so let T equals UH, polar decomposition. And then what do you have? H inverse is equal to U star BU is equal to H inverse AH. I move the H's around. And remember, these are all as considered as sets. This equality is a set equality. So what it is saying is H squared, this is A. If I use the theorem now, H is positive, A is just some subspace. I needed self-adjointness at this step in order to show this step, this equality. So needed self-adjointness of the subspace at this step because I'll take conjugates and I want to ensure that they're still equal. So once I have this, what the previous theorem will tell me is that I can take any power. So in particular, I can take a square root. So this implies H inverse is equal to A. And it also says a little bit more. It's and H to the Z, H to the minus Z is equal to A. So this is for all complex numbers. So in particular, let me just write it suggestively as H to the IT, A, H to the minus IT is equal to A. And these are unitaries. So T belongs to R, H to the IT is a unitary. Okay. So these were some conclusions. Oh yeah, and there is one more conclusion. So keep this in mind. Once we hit Tomita's theorem, you'll see this phenomenon very. So this is one observation. The other observation is U star of BU is equal to A. So here you have a one parameter group of automorphisms of A, so-called. As I change my T, you have automorphisms. Of course, this is invertible. And if I'm composing, you can immediately guess, yeah, it's a one parameter group of automorphisms here. And then you have this sort of relation between A and B. So A and B are unitarily similar. So A and B are unitarily similar. Okay. So now that I have stated the Gardner phenomenon, so-called Gardner phenomenon, what we want to do is actually prove it. So rest of the talk, most of the talk will be about proving this result. Yeah, and by the way, instead of IT, if I had just chosen T, what do I get? H to the T, A, H to the minus T. So then what I would get is things which are still automorphisms, but let's assume that A is some sort of one-Neumann algebra or a C-star algebra, whatever. Like let's say A is a one-Neumann algebra, then this is actually giving you star automorphisms if you choose H to the IT. If you don't choose IT, you just choose H to the T, then you get inner automorphisms, but they're not necessarily star automorphisms. So maybe if you're thinking of Fourier transforms here, then maybe you should think of like a half, like a semigroup and a Laplace transform over there. So, but mostly Tomita's theorem will be concerned with this part, with this one parameter group of unitary action. Yeah. All right. So positive inner automorphisms. Inner automorphisms are like TAT inverse. If T is positive, then it's like a positive inner automorphism. So T is a positive invertible operator. So that is going to be our assumption throughout. And which means sigma of T, first of all, is a subset of 0 infinity, but you can say a little bit more. It is away from 0 because it is invertible. So in fact, you can say spectrum of T is contained in some epsilon to infinity. Okay. Now, the spectral theorem for self-adjoint operators will say that you have a resolution of the identity so that you have something like this epsilon to infinity lambda dE lambda. So this is the resolution of the identity. The spectral projections that you'll get are here. Now I can take a logarithm of this. This is well defined because I'm away from 0. If 0 was in there, there would be some issues, but otherwise I'm good. So this integral, I can say, will go from log epsilon to infinity. Actually, it will terminate at norm of T, but that's fine. I'll just write it this way. So I'll have a log lambda dE lambda. So this is a self-adjoint operator. Okay. So now consider this map. So what's a good notation? Let me call it alpha. Okay. So alpha, I will define it as a map from B of H to B of H as alpha of A is equal to TA T inverse. In other words, alpha is equal to T tensor T inverse. That is the map. And this is just a notation. Alpha to the S from BH to BH is defined as you compose this alpha S many times. If S is a natural number, of course, you understand it's T to the N AT minus N. Otherwise, this makes perfect sense because of the function calculus. I can always talk about the function T to the S. So alpha S is, in other words, this thing, T to the S tensor T to the minus S. This is just notation. Okay. And let's denote the logarithm, which we saw was a self-adjoint operator by L. Then this map add L is defined in the following manner. It's just the commutator. So LA minus AL. So if you're already a little bit familiar with like strongly continuous or even uniformly continuous semigroups, you realize that there are infinitesimal generators. Like you get some sort of derivations and you exponentiate the derivation that will generate the automorphisms. And these are like the inner derivations. So if you have an inner automorphism, you'll get that at the infinitesimal generator at inner automorphisms. So our point here is to say that like the infinitesimal generator of alpha to the S is actually logarithm of T, add of log T. So that's what we want to show first. So, and clearly these are inner automorphism. It's a one parameter group of, in fact, a group of automorphisms. Here, by the way, I should specify S I'm not taking to be a complex number. I'm specifically taking S to be a real number. Later on, we'll deal with complex numbers. Okay. So here's a quick lemma. So the lemma just says that this map is a continuous map. This bilinear map that we have defined alpha to the S, that is in fact a continuous map. So where you have A, B goes to A tensor B. So this map is uniformly continuous, norm continuous, you could say. We are interested in the map T tensor T inverse. Here we are just saying, if you give me two operators AB, I can think of the map which sends X to AXB. So that map is in fact uniformly continuous. The proof is straightforward. All you have to do is notice that AXB is less than or equal to norm A times norm B times norm of X. So in other words, you have A tensor B acting on X is less than or equal to this thing. So it just tells you that the norm bound of A tensor B is nothing but norm A times norm B. It could be smaller, but for now we are happy with it having proved that it is continuous map. Because we are going to do a lot of approximations, so just having this in the back of our mind is good. Okay. So now the next lemma that the claim is alpha to the S is nothing but X of S add L. Again, like if you're already familiar with this will be standard results, but I think it's if you have not seen this, it's good to see that how norm continuous one parameter groups are generated infinitesimally by this. So the idea you can think of is also very much like Taylor series. So what does Taylor series say? F of X plus T or is like F of X plus T times F dash X, what blah, blah, blah. Then this you can think of as a differential operator acting on this. So effectively, you think of translation. So this is translation of this function. So translation by T is nothing but E to the TD, where D is the differential operator, right?
Sir, E tensor B is a map from BH to BH.
Yes, correct.
Then,
this is the map A tensor B.
Yeah, it is not verified. It says BH cross BH to BH. It should be BH cross.
Oh yeah. It's B of H. You're correct. You're absolutely correct. So the question was, so it doesn't look like this map goes to B of H, and that is correct. It actually goes to B of H, meaning now think of this as some Banach space, and you have all these bounded operators from the Banach space to itself. Yes, right, absolutely. Okay, yeah. So coming back to this discussion, if you think of Taylor series, it is just saying that if I have a translation T, it is nothing but exponential of. So D, the differential operator D, is the infinitesimal generator of translations. Generator of translations, and differential operator satisfies Leibniz rule, the product rule, like derivative of F times G is derivative of F times G plus F times derivative of G. And in fact, if you have a nice continuous one parameter group of automorphisms, think of translations as automorphisms, then you will have such an expression, but here this will be replaced by certain infinitesimal generator, which is the derivation. And what this lemma will essentially show is that if you have inner automorphisms, you get the derivation is an inner derivation. Typically, it should have been some delta, some derivation delta satisfying the Leibniz rule, but here you can say more. So that is the lemma that we want to show. The proof is again like it's like proving product rule for differentiation. You just have to follow the steps from first principles. So let's say A is in B of H, and then we're looking at alpha of S minus I of B of H. So alpha S is a map in here, right? B of H. It sends bounded operators on that Hilbert space, two bounded operators on that Hilbert space. It's an automorphism of B of H. So now this divided by S. I'm trying to take derivatives near zero. So I'll send S to zero eventually, but let's say I'm making it act on A. Now I'll look at the definition. What is alpha S of A? It is T to the S, A, T to the minus S, minus A. This is just the identity operator, what takes A to itself. Then I'll do a telescoping, same proof as product rule for differentiation. So minus, what do I want to consider? T to the SA plus T to the SA minus A. So here I have 1 over S, T to the SA, T to the minus A minus identity, plus 1 over S times A. Now limit of S going to 0, T to the S is equal to identity. Now you should ask me the question, which sense? The answer is uniform sense, in the norm sense. That is because T is assumed to be invertible. If T were not invertible, then limits like this will still exist, but they may be in the strong operator sense and so on. So, but since we have assumed T is invertible, this is in the norm sense, uniformly. And we also have limit of S going to 0, 1 over S, T to the S minus identity is equal to logarithm of T. Uniformly, again, this is uniformly, this is log of T, which is by definition, this is our definition of L. It's, think of this as e to the S log T. So derivative of e to the S dds of e to the alpha S at 0 is equal to alpha. So that log T is what you're getting. Just use function calculus and you'll figure this out. So this is also uniform. So if I take the limit of S going to 0, what I'm going to get is, so this will be yeah. So S going to alpha to the S and S going to X. So they have so these are both one parameter groups, have the same infinitesimal generator, which is L, add L. I mean, for that, all you just notice is that when I take S to 0, this anyway uniformly goes to identity. And this derivative 1 over st to the minus s will go to minus log t, and this will go to log t. So it will be log t times a minus a log t, which is just the commutator, which I have written here, right here. So perhaps I should have finished that step. So maybe I will do that here. So limit of s going to 0 of whatever expression we have that here. The first one will be a minus a log t, then plus log ta, which is commutator of log t with a. So here what we have is two uniformly continuous one parameter groups, and they have the same infinitesimal generator. But the thing to notice here is that these are both analytic. So both are analytic, meaning they have power series expansion. This is very clear. All you have to do is do identity on b of h plus s add L, then add L composition with itself, s square over 2 factorial add L squared, and so on. So this is analytic is pretty clear. Here, just to check that it is analytic, all you have to do is do something similar. Think of this as e to the s log t. Now, whenever I have this map, t to the s, t to the minus s, I have a power series here. I have a power series in s here. I can group together the terms. So then I will have like some s to the n here and some operators grouped together here. So this is also an analytic family. And then you have two analytic families. They are completely determined by what happens at their 0, right? If I have two power series, the behavior near 0 is all that matters, the germ, as they call it. The germ of that function only matters. What happens far away doesn't matter. So that is also an observation that one has to make, that these are both analytic families, and then their infinitesimal generators are the same, so they must actually be identical. So alpha to the s is exp s add L. Okay. All right. So yeah, so this whole theorem is a very nice exercise in reviewing all of the Banach algebra basics, like Gelfand, Neumark theory, and so on. It's a very fun exercise. So the next lemma says for S in R, alpha to the S. Remember, this is an operator in B of H. So don't think of this as a Hilbert space operator. There's no really adjoint unless H is finite dimensional or putting some Frobenius inner product. So you have alpha to the S in B of H has a positive spectrum. So first of all, it has a real spectrum, and then it is on the actually right-hand side of 0. Okay. So anyway, without loss of generality, we could have always thought of alpha to the S as being our T, right? So if I just prove it for T, that T has positive spectrum by the same proof, it will hold for any, like S is just telling you where to look at. So without loss of generality, we can just prove this assertion for S equals 1. Okay. So now T we had noted had this again, like I'm replacing the epsilon by 0. Oh, actually, no, I think I should stick with this epsilon. So you have this spectral decomposition of T being positive and self-adjoint. Now, for every n, I can approximate in norm using these spectral projections, like it's a convergence of Riemann sums, right? Once you look at the proof of the spectral theorem, what happens is you're essentially looking at Riemann sums of like finite sums of linear combinations of these projections, and in norm, they will converge to this operator. So those are the Riemann sums I'll be using. So let me call it Qn. So Qn is equal to summation I equals 1 to m, let's say, lambda I ei, such that norm of T minus Qn is less than 1 over n. So I have a sequence now, Qn, involving the spectral projections of T, such that it converges to T. So yeah, so approximation using spectral projection. All right. So what does, so this is invertible. So you can always choose it such that all these lambda is strictly positive. So the inverse of this, Qn inverse. In fact, you can always choose this lambda I so that they're always bigger than epsilon. So in that Riemann sum, just force it. So this is nothing but summation I equals 1 to n lambda I inverse ei. Okay. So what does Qm tensor Qm do? So this acts on X and sends it to sorry. So Qm tensor Q my notation was Qn, right? So Qn tensor Qn inverse X. So effectively, I'm trying to approximate the operator T tensor T inverse by using these spectral projections. So this is nothing but Qx this. And in fact, both of these, because T is invertible, because I'm away, you will notice that Qn also goes to T, Qn inverse also goes to T inverse. All right. And what can we say about spectrum of Qn this? This is exactly equal to lambda I lambda j inverse 1 less than equal to j less than equal to m. So that is, so yeah, so why is that? Yeah, so that is simply because I have to write it out. So Qn, so this was a bilinear map, right? So this I can write as summation I equals 1 to m lambda I ei, and then tensored with summation j equals 1 to m lambda j inverse ej. Now this is nothing but summation ij going from 1 to m, you have lambda I lambda j inverse, and you have ei tensor ej. These, note that these are orthogonal idempotents. So family of orthogonal idempotents in B of H. Idempotent simply because if I do it twice, think of it this way. Like if I apply this twice, I'm going to go to ei squared here, and then I'm going to get an ej squared on the other side. And I know ej's are projections. So ei tensor ej, family of orthogonal idempotents in B of H. And then you have this lambda I lambda j inverse here. So this clearly tells you that you're writing it as a linear combination of orthogonal idempotents. So the spectrum actually must be exactly this, lambda I lambda j inverse. Okay. So now what I will do is take little m to be x inverse y, such that xy belongs to spectrum of T. So effectively what you're doing is, let's say, you can, for example, choose this to be norm of T over epsilon, something like this. Because the smallest possible, like the largest, no, I should do the opposite way, sorry. So choose the smallest possible value for x inverse. So for y, which is epsilon, and then the smallest possible value for x inverse. So then the largest possible value of x, let's say, is bounded by norm T. So this you can use as your little m. Or yeah, so min. Maybe I should say just inf. So infimum is clearly less than equal to this. Then you can use sup. No, I think I said something incorrect. It is bigger than equal to this. Now, if I look at this, then this is less than equal to, you can have norm t over epsilon. So you have this. So just do brute force. Biggest possible of y, you have a bound norm t, and smallest possible for x, you have a bound of epsilon. So 1 over x, the maximum is 1 over epsilon. So you multiply, you get this upper bound. So here, this is the main thing we want is this is actually bounded away from 0. This little m is actually bounded away from 0. So now we'll go back to our first courses on Banach algebras. So look at, look at the commutative Banach algebra generated by these qn's and t. Algebra generated by these approximating sort of operators by qn tensor, qn inverse, and t. We are putting all of them together. Of course, they commute because all those projections commute, hence those bilinear sort of operators commute. Okay. So what I want to claim is that t has, so what did I really want to prove? That this alpha s, oh, no, sorry, my bad. Yeah. I meant t and tensor t inverse. You're right. Not t, but rather t tensor t inverse. What we want to prove is that this has positive spectrum. What we know is that this has positive spectrum, right? So then we want to use a theorem which says that if I have a bunch of operators converging to another operator and the spectrum of all of them is positive, I want to use some sort of continuity of spectrum. But in general, it is not true. In fact, in B of H, you can have a sequence of nilpotents or quasi-nilpotents, let's say. So quasi-nilpotents all have spectrum 0, right? Just a singleton set. But that does not mean the limit also has to have that. It is also a very classical result. A lot of people worked on it, Helmers, Herrero, and all this. So sequence of quasi-nilpotents did not uniformly converge to a quasi-nilpotent. And in fact, it has to contain 0. You have some sort of, is it lower semi-continuity? Like you have some one-sided continuity for the spectrum. For normal operators, you have continuity of spectrum. But in general, this need not be true. So sequence of quasi-nilpotents can actually, the convergent part may have even like something like a disk as their spectrum. As long as it is connected and contains the origin, and then you have some index obstruction, then you can have it as a norm limit of quasi-nilpotent operators. So this phenomenon is not generally true. Just because Tn goes to T doesn't mean spectrum of Tn goes in the Hausdorff distance, let's say, to spectrum of T. But here, of course, I cannot talk about normality or anything, right? Like I said, I am on B of H. B of H is not a Hilbert space. I'm just thinking of it as a Banach space. But if I'm in the commutative Banach algebra setting, this is still true. And this just follows by looking at the Gelfand transform. So I hope you remember the Gelfand transform. If you have a commutative Banach algebra, if you look at maximal ideals, and then you have this quotient map, which will give you a multiplicative functional. So if rho is a non-zero multiplicative functional, we know that its image contains things in the spectrum. Rho of A is element of the spectrum. So non-zero multiplicative functional. Then maybe I'll quickly remind you how that proof goes. So if you just look at this is just 0, right? So this clearly tells you that this belongs to some ideal, so it is not invertible. So it belongs to the kernel of this row. Okay, so that's the proof. So non-zero multiplicative functional. Rho of A belongs to spectrum of A. And you have that the Gelfand transform. So you in fact have the norm is less than equal to 1. Rho of A will always be less than equal to norm of A because of the spectral radius formula. So rho of A is in the spectrum and spectral radius is bounded by norm of A. So you always have this. So if I have AN goes to A in a commutative Banach algebra, so just a reminder, we are in the setting of a commutative Banach algebra. Then what I have is rho of AN minus A is less than equal to norm of AN minus A. So that means rho of AN goes to rho of A, right? So this is for all non-zero multiplicative functionals. So if I vary my row, so effectively what I have is in our sequence in Qn tensor Q in inverse, row of this belongs to 0 infinity for all n and all row, right? So it belongs to, because we saw that the spectrum is in 0 infinity. So for this is true for any n, and simply because of that, using this Gelfand transform, that the image, in fact, as you vary over all non-zero multiplicative functionals, you get all the elements of the spectrum, right? Given any element of the spectrum of this, you can find a row such that this is equal to that value. So having known this and using this continuity, what do we conclude? That row of A belongs to 0 infinity for all row. This implies spectrum of A is contained in 0 infinity. Oh, sorry, why am I writing A? Let me erase this. What I want to write is T tensor T inverse. So row of alpha, which is T tensor T inverse, alpha to the 1, if you like. So then spectrum of T tensor T inverse is contained in 0 infinity. And you can just repeat the same argument for T to the S. Like we just use the fact that T is a positive operator and did the spectral projections. You can do the same argument for T to the S. So that's why I said loss without loss of generality. So we are done with this proof that alpha to the S has a positive spectrum. Okay. So next proposition is trying to approximate that infinitesimal generator add L using polynomials in alpha with real coefficients, in fact. So there is a sequence of polynomials Pn with real coefficients satisfying limit of n going to infinity Pn of alpha. Remember, alpha is a map in B of H. Pn is again a map in B of H. So this add L is equal to 0. So we are able to approximate add L using alpha. So, I mean, just as a reminder, the main thing that we wanted to prove is Gardner's invariance theorem, right? So effectively, what we are looking at is if alpha, something is invariant under alpha, it is also invariant under polynomials in alpha. So effectively, we want to reach the conclusion that it is also invariant under add of L, and which would mean that it will be invariant under multiples. Then you exponentiate, it will be invariant under that also. So that's the game that we're playing right now. So that's why we need this approximation theorem. And as you can guess, it's purely talking about holomorphic function calculus and such. So you have 0 here, you have little m. Remember, little m was you looking at those ratios of things in the spectrum of T, which was corresponding to alpha. This was the lower limit and upper limit. And then, of course, there's a midpoint. Okay. So what you know that add L kind of looks, so L kind of looks like log of T, right? So you want to use the power series expansion of logarithm and then approximate it using polynomials. So on this interval, you do have a logarithm function, right? Because it is away from 0, it doesn't contain like the negative real line. You can choose one version of the logarithm on this. And for simplicity, you can just think of, I'm not going to interpret it in terms of little m and m. You can normalize them the right way, but you do know log of 1 plus t is, I guess, t minus t squared over 2. Yeah. T minus t squared over 2, t cubed over 3, and so on. These are real coefficients. Remember, I'm talking about things with real coefficients, right? All of these are real numbers. So now I can expand this around all of these and still have a power series expansion z minus z squared over 2, which has all real coefficients. Okay. So yeah, no. So now I want to take logarithm of add L, really. Yes, so this was for alpha. So effectively, this allows me to take log of alpha. Yeah, right. So log of alpha is kind of supposed to be like log of t. So it is supposed to be like L. Okay. So yeah, I think there's something missing here, but we'll figure it out very soon. Okay. So anyway, we have a sequence Pn, just truncating this, you have a sequence Pn so that Pn of Z goes to this. So this is a logarithm. So logarithm of Z. So I'm just choosing one such branch and calling it a logarithm. Pn of Z goes to lambda. Then what I have for Pn of alpha is that it goes to no. So I'm missing something. Right. So I have Pn of alpha. Yeah, right. Yeah. So what I have done is chosen Pn to be, let's say, t minus t squared over 2 and all the way up to -1 to the minus n over. So this is the polynomial I've chosen, Pn. Now what I do know is Pn of alpha. So this is a logarithm of alpha. Forget about add L for now. I'm not saying anything about add L. That was creating some confusion in my mind. Right now, I'm not talking about add L at all. All I'm trying to do is taking a logarithm of alpha. Eventually, I want to show that, because the whole problem here is that I'm making a choice of a logarithm. If I had a function, then I would say, okay, there is a 2 pi I difference, but here I have operators, right? So it will differ by a summation 2 pi I times idempotent. So I want to take care of that. So at this stage, we can say that, okay, this difference is like a linear combination, like integer linear combination of idempotents, but that does not mean the norm goes to 0, right? Idempotents don't have 0 norm. So that's why that's the confusion. So until here, add L has not made an entrance. So we are just saying that I am able to approximate this logarithm function using polynomials. And then I'm just applying that using holomorphic function calculus on alpha. That's all. So Pn of alpha goes to a logarithm of alpha. Now we know that alpha has real spectrum. In fact, it had positive spectrum, right? So what can we say about Pn of alpha? Again, real spectrum, right? Because of like the spectral mapping theorem, right? Pn. So here we use the fact that it has real coefficients. These coefficients were all real was used here. So Pn alpha has real spectrum. Now again, using the same argument, we have these commuting family. Just look at the Banach algebra generated by this. So this implies this has real spectrum. Okay. And this implies x of, if I exponentiate this, so you have a self-adjoint, sorry, why am I using self-adjoint? Here we are not in the Hilbert space setting, it's just an operator in B of H. So again, let me remind myself. So this has real spectrum. And if I exponentiate, again using the spectral mapping theorem. So all of these steps, this step maybe you can call a simpler version called the polynomial mapping theorem. So we are just using here and here spectral mapping theorem. So the spectrum of x, this is just exponentiation of the spectrum of this. And since this has real spectrum, the exponential will be positive, right? So this has real spectrum, and even more strongly in here. Now we define this D, which is the closed subalgebra. So it's a Banach subalgebra of B of H. B of H generated by add L and I of B of H. So identity. So add L and this. Yeah, so D is the subalgebra generated by add L and this. So what we really want to show is this add L. In fact, this lambda is equal to add L. That's what we want to show. Then that will finish the proof that P and alpha in fact goes to add L. Okay, so D contains any holomorphic function of add L, right? If I have a Banach algebra, it contains an element A. If I take any holomorphic function of A, the same Banach algebra contains it, holomorphic function calculus. But exponential of add L is nothing but alpha. So D definitely contains alpha. This implies D contains polynomials in alpha, P and alpha. This implies D has to contain lambda. So the moment D contains add L, automatically you get that it contains lambda. The question is whether lambda is equal to add L. So here I'm going to appeal to a theorem known as Lorch's theorem. Also, the proof is not very hard, just basic resolvent theory, but it's a very nice theorem. It kind of tells you that it's like saying which complex numbers have exponential equal to 1. We know that it forms some sort of lattice, right? 2 pi I. So not a lattice, but what I mean is you just take 2 pi I n on the real line. So it talks about a Banach space version of that. So in a commutative Banach algebra, x of p, so we're trying to find logarithm of the identity function. Just like in complex numbers, I said, you want to find logarithm of 1. What are the logarithms? You have e to the 2 pi I, e to the 4 pi I, 6 pi I, and all those things. And 0, e to the 0 also. So integer multiples of 2 pi I. So similarly, we want to figure out what operators, if you exponentiate, you get identity. Okay, so this holds if and only if P equals summation. So 2 pi I, of course, there's a term 2 pi I.
The identity is the identity of the Banach algebra.
Yes. Oh, okay. Yeah. Thank you. Yeah. So in a commutative Banach algebra, if this is, so this is equal to identity. So this is the identity of, this commutative Banach algebra. So it will be applicable to our special case where that E will be I of B of H, but you're right. So this is equal to E if and only if P equals 2 pi I times summation, let's say nu equals 1 to K, N nu, J nu. So these are integers. So N nu is not equal to 0. If it is 0, I mean, I don't even bother containing that, like writing it out. Integers and J nu are mutually orthogonal idempotents. So effectively, these are things which have spectrum 0 or 1. So effectively, N nu times this is like things which are taking value N nu or 0. So at a given vector, let's say, so it's you are able to make so many choices of when to choose e to the 2 pi I, where to choose e to the 4 pi, but that's all. So this theorem is telling you it's the logarithm of 1 has a very nice description, simple description using mutually orthogonal idempotents. Okay, so we're going to assume this and proceed. Okay, so using that, what can we say about gamma minus add L? Exp of this, these commute, by the way. These are in the same D, which is a commutative Banach algebra. So if they commute, we can write it as this times add L. But this exponential was what? It's just alpha, right? Both of them are equal to alpha. This is also equal to alpha. This is equal to alpha inverse. This is literally the identity of B of H. So from this Lorch's theorem, what we have figured is that, okay, I mean, lambda has to be equal to add L, but modulo certain things like this. 2 pi I times summation N nu J nu equals 1 to k. I mean, J nu you can think of as Rees idempotence because you already know that by spectral mapping theorem, the spectrum has to be discrete. It has to be only on those points, e to the 2 pi I n. And then you take a contour around it and find the Rees idempotent and so on. So yeah, the proof is not too hard or technical. It's very intuitive and very nice. Okay. So you have this. All we want to prove is that this part actually is 0. Then we'll have lambda is equal to add L. Now pick rho. So again, we are going to use Gelfand transform. So let rho be a non-zero multiplicative functional on D. So D is a commutative Banach algebra. So which was generated by add L and the identity. Okay. So what can we say about rho of x of S this? This is real. I mean, so this we had proven that the spectrum is real. And rho of x of S add L is real. So which means, and we know that since you have an idempotent, this is 0 or 1, right? These are the only choices you have, simply because rho of J nu is equal to rho of J nu squared, which by multiplicativity is rho J nu whole squared. So for idempotent, the only value you can take, it's essentially expressing the idea that only things in the spectrum of an idempotent are 0 or 1. That's all. Okay. Now note that exp to the S lambda. So this actually needs a little bit of a computation. So lambda is given to be this, right? Right here, you have this expression. I'm just taking, exping it out. Exp of S, I'm multiplying S and exping it out. So it's exp of S add L times I B of H minus summation nu equals 1 to k J nu plus summation nu equals 1 to k e to the 2 pi I n nu J nu. So you just have to look at the power series. Anyway, it will be multiplication of this times this. This all commute, right? X of S times this is X of S times this times X of S times this thing. Now, how to expand this out and using the power series expansion of J and the fact that any power of J is same as itself. So you have to manipulate a little bit because when you do an X of J nu, so let's say I do this, what do I get? I get I plus J nu plus 1 over 2 factorial J nu and so on. So you would want to, like, if I add a J nu here, then I get an E term, right? So all the powers are just J nu. So I can write it as 1 plus, so 1 minus J nu plus J nu, right? And then I take 1 plus 1 over 2 factorial and so on, right? So I get 1 minus J nu plus E times J nu, right? Something like this. So this is the computation I have to do because this is not a J nu, it's a 1. So I have to move things around a little bit. So it's a very similar computation to that. So you get identity here, a lot of ones. That's the identity operator. And then you have a summation J nu you get from this part. And rest of it will be summation nu equals 1 to, because I just took without the 2 pi I n term. Otherwise, I would have to include that here. So you'll get e to the 2 pi I n nu. Okay, so I hope you believe that. So now this rho of this has to be real, right? We just noted it here. Rho of x s lambda is real. Rho of x s add L is real. And rho is a multiplicative functional. So writing it out, what we have noticed is rho of x s lambda is equal to rho of x of s add L times rho of whatever quantity we have here, which is I of B of H minus summation rho of J nu 1 to k plus summation nu equals 1 to k e to the 2 pi I nu n nu, sorry, this is the integer, and then rho of J nu here. Okay, now this is real, this is real, so of course this has to be real, and these are actually non-zero, these are actually strictly positive. So x s lambda, the spectrum is strictly positive, so these are actually strictly positive numbers, so I can divide things out. So I have that this is real, so this thing is real for all s. Note that there is an s here, that is key. The fact is there is an s here for all s in R. Now, effectively, if that is possible, anyway, these are real numbers, rho of j and nu, and these are all real numbers. If this were true, then effectively it is like saying, of course, if rho j nu is 0, what I can do is just truncate this sum. But there is a sum such that e to the 2 pi s nu is real for all s. Is it possible to have that? You have a bunch of finitely many trigonometric polynomials, and I add them, and I'm saying that their values are real for all s. That is not possible. Simply because if their values are all s, so let me call it f, then so f is a real valued function. I mean, you can just use an intermediate value theorem sort of argument. So how do you prove this? So I'm just trying to say that if I have a bunch of trigonometric polynomials which I'm just adding up, then they have to. I mean, looking at so those are the Fourier series coefficients. You have real coefficients here. No, and nu. Yeah, I mean, this is possible if you have the cancellation. If you have nu and minus nu. Okay. Sorry. F is analytic, right? No. What I'm saying is this can still be true if you have a nu and a minus nu. Then the imaginary part will cancel off. So I want to say that nu. Oh yeah, right. I think in this part, nu is bigger than 0. P is no, but you can always multiply and minus 1. Okay. Yeah, I think there is some estimate you can use. Oh yeah, right. So these are mutually orthogonal idempotents, right? So I can choose a functional. Yeah. I have separating multiplicative functionals, right? So I can choose such that one of them is 1 and rest are 0, right? Because so in that case, okay. I mean, I don't think we should waste too much time here, but the idea is to show that like this part actually must vanish. So maybe I'll talk about it next time. Let's not waste too much time here. But then using this fact, you will be able to show that this part actually has to be 0. All the nus must be equal to 0. Okay. And then if you look back at the definition, what you'll get is lambda is equal to add L. So there is a question mark here. So maybe I'll revisit next time. Okay. Yeah, so there is still one small step remaining. It's not that nu is equal to 0. It's more like rho of j nu is equal to 0 for all rho. So yeah, you must have, so the conclusion will be that if n nu are not equal to 0, so that will be a contradiction. So effectively, you must have rho of j nu, because we're arguing at the level of complex numbers, right? No longer at the level of operators when I'm using this argument. So the conclusion will be that either this is 0, but then nu we have assumed to be not equal to 0, or you have rho of j nu equals 0 for all rho. But j rho belongs to the radical of the Banach algebra. So if this is true, this is the definition of the radical of the Banach algebra, is the intersection of the kernels of all these maximal ideals, right? Of D. Now, the only idempotent that can be in the radical is actually the zero idempotent, because there are other, like this is also equal to the Jacobson radical, where you have like 1 minus xr is invertible for all x. So r will be the radical if 1 minus xr is invertible for all x in D, right? But in particular, just choose j nu, right? So essentially it's saying 1 minus j nu is invertible. So yeah, so if j nu belongs to the radical, that means j nu cannot have any sort of one part in it. J nu must actually be identically equal to 0. So from this fact, you conclude j nu has to be 0. So either you have all the n nus are 0, or you have all the j nu must be 0. So there are two parts to it. So either n nu equals 0 or this. Okay, so I'll hold this because some of you are taking notes. I'll hold this for a minute. So now we have all the ingredients that are ready to prove our main invariance theorem. So yeah. So the invariance theorem said that if we have TST inverse is equal to S, so here what was S? It was norm closed subspace of B of H, and then T was some positive invertible operator. The corollary involved arbitrary invertible operators. So this was just a positive invertible operator. Then what we wanted to show is that, so the conclusion is this is also equal to S for all complex numbers Z. So the proof goes as follows. So look at this set B. So there's a lot of B's here. So the set of elements of B of H leaving S invariant. So look at all those operators from B of H which leave S invariant. So this is a norm-closed subalgebra, right? It's a closed subalgebra of B of H. Because if I have a set which, if I have an operator which leaves us this subset invariant, and then I compose it with another such operator, then again that will leave that subalgebra invariant, a subspace invariant, sorry. Okay, so this is a close, and again you just use the standard closure arguments, approximation arguments. But this thing contains add L, right? Because TST inverse is S, which means if I look at polynomials in T, they will leave S invariant, which means I have shown that I can approximate that. That is exactly the content of this previous theorem. That's what you're using here. That I can approximate add L using polynomials. So if alpha leaves something invariant, add L also leaves that invariant. So I have a norm-closed subalgebra which contains add L, in particular any multiple of add L. I times add L is also in there. So in fact, Z times add L for all Z belongs to C. So it contains this. So this implies, so I mean, the proof is pretty much done. So this implies it contains X of Z times add L, simply because here again you have a power series expansion and each of the elements in there are leaving S invariant. So XZL is in that space B of HS. Okay, and this is nothing but T to the Z tensor, T to the minus Z. So it boiled down to the previous theorem, approximating add L using polynomials in alpha. Okay. Then the corollary we had already noted. If you have self-adjoint subspaces, in B of H, and T inverse is equal to B. So T is just some invertible operator. Then, just to summarize, what we had was H to the Z, A, H to the minus Z is equal to A, and U star, or I should write, since I'm writing UA U star is equal to B, where T is equal to UH, polar decomposition. So similarity, kind of similarity between A and B implies unitary similarity. And also it is, as a byproduct, also giving you a 2-parameter group of inner automorphisms, 2 parameters given by the complex numbers, 1 parameter group of star automorphisms, if I choose just Z to be purely imaginary number, right? So now in the remaining 10 minutes, what I will do is make the connection with Tomita's theorem. And we'll just talk about MNC, matrices here. Okay. So let's say I have H is MNC with a Frobenius norm and the Frobenius inner product. So it becomes a Hilbert space. So this has a distinguished vector, which is the identity. And the action of, let's say, MNC acts on H by left multiplication. By left multiplication. So essentially, I mean, we did the GNS construction. That's exactly what's going on. You're doing some sort of GNS construction, but it depends here. If I'm doing the Frobenius norm, I have chosen the functional on MNC to be the trace. If I chose any other operator, this norm will change accordingly. So we're just first taking a look at the usual thing, like you're looking at the tracial functional, and then you're doing a GNS representation. So the Hilbert space looks like this, and there is a distinguished vector I, and that means I is actually a cyclic and separating vector for this representation. Separating vector for MNC, and that is because the way we have made things work is it's looking like a left regular representation. You can actually very carefully try to check. Cyclic is just the way anytime you do a GNS construction, you just get a cyclic vector out of it. When you convert your state rho into an equivalent vector state, you get that vector state is a cyclic. Separating, you can verify. Okay, I mean there is a theorem you can use about commutants and so on, but we'll talk about it, but not today. All right. So now that the previous discussion was going one layer up, B of H is operators from H to H. B of H was operators from B of H to B of H. We are going to do something similar here. We're going to define an operator S from H to H. So H, remember, is MNC, but I'm writing H because there are two MNCs floating around. One MNC is a Hilbert space, one MNC is a C-star algebra. So that's why I want to specifically mention H when I'm interpreting it as a Hilbert space. So there is a map which sends A to A star. So A is a vector in this Hilbert space. It is sending it to another vector in the Hilbert space. So one thing to note is, what is S square of A? So first you get S of A star, you get A star star, so you get A back. So as an operator from H to H, so think of this S as belonging to B of Cn. If you're thinking of this as MNC, this is in B of that. So that's what's going on. This is MNC, this is MNC. You have a map from MNC to MNC, which is SA equals A star. So what we have is S square is identity. So identity of B of H, which is B of Cn. So you have S square is identity. It's a very, very distinguished sort of. So why do we care about this? Okay. Now let's say T belongs to B of H, and by the way, we have some distinguished operators in B of H. So there is a multiplier operator from H to H. So MA belongs to B of H, where A belongs to MNC. I'm not writing A belongs to H, I'm just writing A belongs to MNC. So the multiplier operator, what it will do is you give it B, it will spit out A times B. It's a left multiplier. You give it the vector B and the matrix A, where B is a matrix sort of vector. Then you just multiply AB. Now think of this as a vector, not as a matrix. Think of this as a vector, but this as a matrix. So MAB is M. So now we want to figure out what things, like what the commutant, so-called commutant, looks like. So you have TMA equals MAT. Let's say for all A in MNC. So for all A, you have this multiplier operators, and let's say we're trying to look at this T. So we do a few quick computations. So the claim is that okay. Okay, and this distinguished vector, let me call it a U vec. So now SMAU, so U is just identity, but I want to think of as a vector. So let's look at this inner product, TU. Now this you should be thinking of this as a trace. So these are matrices, right? As considered as vectors in the Frobenius inner product. So this is just T acting on I left multiplication. It's just T. This is just S of A. So this is A, this is A star. This is A star inner product with T of U. Yeah. So then I want to think of it as T star MA star U dot U, which is the same as MA star T star U dot U. Here we're using the fact that T commutes with MA. I didn't prove it yet, but maybe you can take it as an exercise, because this will take a little bit of getting used to, because this star and this star don't mean the same thing, right? Here MA is acting on H which we have made into a Hilbert space. So this adjoint is acting as a mapping in B of H. Here this B of H is a Hilbert space. So but you take it as an exercise to show that MA adjoint is equal to M of A star. And then this is also commuting with T star. And then you have, this is equal to T star U MAU, then there will be a bar, simply because this is actually not a linear map. It's a conjugate linear map. Because when I multiply lambda here, lambda A will go to lambda bar A star. So when I'm talking about adjoints and all that, I have to keep track of that conjugate linear map. I have 5 minutes. I think I'll redo this more systematically, because I'm also in my notes, my computations are all over the place. So I have also forgotten which comes after what. So anyway, instead of trying to struggle through this, the connection I want to say is that that S, maybe I can just prove this. Yeah. So what I want to say is that if you look at this set, so when I'm looking at representation of A, it is through multiplier operators. So this is the set of all these multipliers, MA. So what I want to say is that it is commutant of this. And that should be easily checkable. So let's do that. So SMA, SMB. So I want to show that whenever I choose an operator in here, SMA, SMB must commute with this, right? Then it will show me that this is in the commutant, right? So I want to show that this is equal to MB, SMA, S. So let's apply it on a vector. I want to show that this is a map in B of H. As a map in B of H, it is true. So I will apply it to some vector in there. So let me call that vector C. So the way MB acts on this is SMA, S, BC first, then S will do a star to it. So you have MA, C star, B star. Then MA will do a multiplication here. So you have A, C star, B star. Then again, S will do an adjoint to it. So you have a B, C, A star out of it. So this left-hand side acting on a vector C just gives you B, C, A star. Now let's compute the right-hand side, maybe on a fresh page. So MB, SMA, S acting on C. So first, you get a C star. The next step, you get multiplication by A. So you get a AC star. Then what you get is MB times a CA star, and you get a BCA star. Do they look the same? They do, right? So what we have shown is that SMA, S is in fact the commutant. But we also saw that S square is equal to identity. So I can replace this as in S inverse. So I have two self-adjoint subspaces. So MA is a self-adjoint subspace of B of H, which is B of Cn. And MA commutant is also a self-adjoint subspace of B of H. What does our invariance theorem say then? Then there is a unitary operator. So if I decompose this as Z to the J times delta to the half, this is a polar decomposition. Then I must have J of MA of J is equal to, first of all, MA prime I mean, I should include a star, but it will turn out that you can easily check from the S square equals identity that J will be equal to J star. There is a few things to check because of that thing I said. The map is not linear; it's conjugate linear. So J, in fact, will not be. So S is not really a linear map, but the polar decomposition theorem still holds. Here, in fact, you'll get delta is a positive map, and J will be some sort of isometry, but conjugate linear isometry. So those things we'll be careful about. But right now, roughly think of it that way. So JMA J star is this, and delta to the IT MA, delta to the minus IT is equal to MA, right? That was the corollary that we had. If we have A and B, such that TA T inverse is equal to B, and you do a polar decomposition, you have first of all A and B are unitarily equivalent, implemented by the unitary part of T. And then if you look at H to the IT, A, H to the minus IT, it's an automorphisms, star automorphisms. So this is really the statement of Tomita's theorem. It just says that if R is a von Neumann algebra with a cyclic and separating vector, then if you look at this map, you define it, then you have this partial isometry J, JRJ. So I'll write it suggestively, is equal to the commutant. And then you have this one parameter group of automorphisms, which gives you R. So it saves R. So this gives you the one parameter automorphism group. Of course, we have not proved it. In fact, the key fact is dealing with unbounded operators and very carefully doing this. So I'm not going to say that, okay, I mean, it's obvious from here on. That's not true, but at least now you see a path. Like why exactly is the Tomita phenomenon happening? So this I'm going to call the Tomita phenomenon. So already, and then we'll look at, so next time maybe we'll start looking at the KMS condition also for states. And that also we can do it to the level of matrices. In fact, in physics, it already arose like the KMS condition with respect to state at the level of matrices. So we'll look at that, and then we'll crank up our gears. Like we'll actually go talk about unbounded operators. Like we'll leave it in our memory. We'll go in a digression, talk about unbounded operator spectral theory and so on, and then come back and prove the full Tomita theorem, like maybe 2 or 3 weeks from now. Okay, any questions? This is where I would like to end my talk. Yeah. Okay, so I hope people are still there. If there are no more questions, anyway, like next time we can stop sharing. Okay, all right. So then, yeah, see you next week. See you next week. If you have questions, email is fine. Anyway, the YouTube videos will be there. You can rewatch if you like.